In this video, we're going to continue the exercises in 1210, where we're just practicing approaching these multi-step synthesis exercises. So if you look at these two molecules in E, and you compare them, you'll see that on the left we have sort of 4 carbons with a methyl group on the second. And in the molecule on the right, we have 1, 2, 3, 4, oh my gosh, 5 and 6 carbons with a methyl group on the second one. So we have more carbons on this molecule on the right than we do on the left. And what that means is we're going to need a couple things. We're going to need a terminal alkyne that we can turn into a nucleophile. It becomes a nucleophile when we add sodium amide. And then the second thing we need is an alkyl halide that nucleophile can do an SN2 reaction with. Okay, well, the question is, do we want this starting molecule to be the terminal alkyne, or do we want it to be the alkyl halide? Because really only one of them will work, and in the previous video we saw a couple examples of why, of how. Because sometimes if you turn a molecule into the terminal alkyne, the triple bond will get buried in a symmetrical place. Both of the carbons in the triple bond will be equally substituted. They'll both be secondary. And that means that you won't be able to walk the reactive part of the molecule from one end of the molecule to the other. So the hint of whether this needs to be the alkyl halide or the terminal alkyne, that comes from where the reactive part of the molecule is. The alkyne, the reactive part of the molecule, is between carbons number 5 and 6. And those carbons are not on this molecule. That means that it would be most efficient if we took that and introduced it as a separate molecule with carbons number 5 and 6 on it. We could take that could be our terminal alkyne, and that means that we'll want to turn this molecule into our alkyl halide. We'll want we'll want a leaving group, a halogen, on carbon number 4 that carbon number 5 here will be able to attack as a nucleophile. Okay, so we can take this molecule and if we, and what we want to do ultimately, like our dream, our long-term goal, is to put an alkyl halide on carbon number 4. Because if we put an alkyl halide somehow on carbon number 4, so we put a halogen there, sorry, a leaving group, if we create this molecule, right, so just working backwards, if we sort of like think, well, we want to make this, if we have this alkyne, and we turn it into a nucleophile by treating it with sodium amide, right, that would rip one of these hydrogens off, and the electrons in that bond would become a lone pair, which then would act as a negative, would have a negative charge and act as a nucleophile. If we had that, what carbon chain would we need? We would need this carbon chain here, and you'll notice that's what we have here. We just need a leaving group on carbon number 4 so that when this nucleophile attacks, the leaving group will leave. And we also need a halogen is perfect for that because it also makes this bond slightly polar. The bromine is electronegative, so it pulls electrons to itself, the carbon becomes slightly positive, and that attracts this nucleophile. So if we had this alkyl halide, then we would be able to make this final product. So notice what we're doing here. We're starting our thinking with the product rather than with the reactant. So ultimately we want to turn our reactant into that alkyl halide. And when you compare them, what you'll notice is that the reactive part of the molecule changes position. In the starting material, it's between carbons 2 and 3. And in what we want, it's on carbon 4. In other words, it moves to the right of the molecule. We've seen how to move the reactive part of a molecule from one end of a molecule to the other in previous videos. It's by doing a series of addition and elimination steps and being careful about Markovnikov or anti-Markovnikov for the addition, and then bulky base or skinny base for the elimination to control where the electrons move. Ultimately, we want these electrons to move to the right side of the molecule, to carbon 4, where our leaving group is. So, first thing we can do is in addition. We'll want to add some sort of a leaving group, because whatever we add is going to go on carbons 2 and 3, and those don't have anything on there. So we want to add something that can be taken off, a leaving group. So HBr is a good choice. Now the reason why you wouldn't want to use Br2 is because that would put 2 leaving groups on. Unless you're trying to make an alkyne, don't do that, because then you give yourself twice as much work to do. You have to eliminate both of the leaving groups. That's easy if you want to make an alkyne, but not if you don't. So here we're just going to add one leaving group, HBr. Now this by itself would be Markovnikov addition. So let's zoom in on this. Think about the substitution here. Oops. This carbon number 2 is bonded to 1, 2, 3 other carbons. So it's tertiary. Carbon number 3 is bonded to 1, 2 other carbons. So it is secondary. We want the bromine to add toward the right. We're trying to move it. We're trying to remove the bromine to the right. So we want to add it to add to the right. That's the secondary carbon here. This secondary carbon. Which means we want the hydrogen to go on the tertiary, the more substituted position. That's the anti-Markovnikov product. So to get the anti-Markovnikov product, we just have to add peroxides to do that radical reaction. Now, that will give us the bromine on carbon number 2, and a hydrogen on carbon on the other carbon. I'm sorry, a bromine on this secondary carbon, and a hydrogen on this tertiary carbon. I'm not going to draw that in just because I want this structure to look cleaner and clearer, but it is there, it's just implied in the skeletal structure. Okay, so we did anti-Markovnikov addition at HBr. That's going to help us move the electrons to the right of the molecule in order to make the alkyl halide that we want. So now we want to move it again. We're going to do an elimination step. This bromine is not there in the product. We have to eliminate it. We want to eliminate it in order to create the double bond toward the right side of the molecule. So ultimately we want to create this double bond. Now that's clearly an elimination reaction, and so we know we're going to have to use a base. But if you look at your original molecule and you just think about that separated from this, you just sort of separately think about it in the context of elimination, the carbon that has the bromine attached to it is the alpha carbon, and each of the carbons next to those are the beta carbons. When you do an elimination, you could form a pi bond to either of the beta carbons. Oops. So you could either eliminate the bromine and create the pi bond to the beta carbon on the left, or you could eliminate the bromine and form the pi bond to the beta carbon on the right. So between the alpha and beta carbons, but because we have two, there are two possible places where you can form that pi bond. If you look at the carbon on the left, the carbons in the double bond are bonded to 1, 2, 3 carbon chains. So that's tri-substituted. If you look at the carbon on the right, the carbons in the double bond are bonded to just 1 carbon chain. So that is mono-substituted. The more substituted product is technically more stable. It's called the Zaitsev product, but it's more crowded. The less substituted product is technically less stable, but it's less crowded. It's called the Hofmann product. If we compare those two with what we want, you'll see that what we want is the Hofmann product. We want to form the pi bond in the less crowded, toward the less crowded carbon. And to do that, what would prefer a hydrogen from the less crowded beta carbon? Because remember, the way this works is the base comes in and steals this hydrogen, the electrons go toward the leaving group and kick it off. What type of a base would prefer a less crowded hydrogen? A bulky base. So to get the Hofmann product, you use a bulky base. The bulky base you'd want to remember is potassium tert-butoxide, TBU. Okay. And what that looks like is a tert-butyl group with an oxygen that has a full negative charge and the potassium is stabilizing it. Notice this big, bulky tail that will prevent it from reaching any hydrogens in this more crowded environment. So it'll only steal the less crowded hydrogen. Okay. So that will give us this alkene. So we've made some progress. We've moved the pi bond over, but now we want to turn that into the alkyl halide that we've been dreaming of since the beginning of this exercise. We want to add a bromine onto that carbon on the end. Not only that, but we also want to add a hydrogen on the less on the other carbon. Now, if you notice this carbon here only has one carbon on it, so it's only primary. The other carbon is secondary. And so here you want to add the bromine on the less substituted carbon, and the hydrogen on the more substituted carbon. If the hydrogen goes on the more substituted carbon, that is anti-Markovnikov addition. So we want HBr, but anti-Markovnikov, so you add peroxides. So that would accomplish that transformation. We would finally get this product, and we can react it with our terminal alkyne. So overall, to create this transformation, you would want to turn this carbon molecule that they give us. What we noticed was the number of carbons increased, so we know we had to use a terminal alkyne and an alkyl halide. We saw that the reactive part of the final molecule was between carbons 5 and 6, which wasn't on the original molecule. That's carbons 1 to 4. So 5 and 6 will be the terminal alkyne, and carbon 4 would have to be turned into the alkyl halide. So we needed to get a halogen on carbon 4. To do that, the reactive part of the molecule to begin with was between carbons 2 and 3, so we had to walk it over to carbon 4. First, we added HBr, and we did that through a series of addition and elimination reactions. First, we did an addition. We have a pi bond. That's the only type of reaction you can do with that. We did anti-Markovnikov addition to get the bromine on the less substituted carbon. Then, we used a bulky base to do an elimination toward the less substituted carbon. Then, we did anti-Markovnikov addition again of HBr to get the bromine again on the less substituted carbon. Finally, once we had that, we took ethine, those 5 and 6 carbons, we treated it with sodium amide to turn it into a nucleophile, and then we had it react this carbon chain here. React with that. So overall, the recipe you would want to hand to somebody who wanted to know how to do this would be use HBr and peroxides. That'll give you this haloalkane. Then do the elimination reaction with potassium tert butoxide. That would give you this. Then anti-Markovnikov addition again of HBr, in the presence of peroxides. And that gives us our haloalkane here. Then we would have to add to that ethine with some sodium amide to make it a nucleophile. That would do the SN2 reaction we'd want, and we'd have our product. Although anytime you use sodium amide, it's always a good idea to do a water wash afterwards, because some of the sodium amide could steal off that terminal hydrogen, so you could do another proton transfer there to stabilize that, put that back on. And that series of steps, that recipe, would accomplish this transformation. In F, what you'll notice if you look at the exercise, the reactant on the left and the product on the right, is that the number of carbons changes. In the left, we have that 6-membered carbon ring, the cyclohexane. That stays the same in both of the molecules. But if you look at the chain attached to it, in the molecule on the left, there are 2 carbons. In the molecule on the right, there is only 1. So we lost a carbon. We removed a carbon from the carbon chain. And we only know one way to do that. That is with ozonolysis. So we're going to have to do ozonolysis. Let's think about what molecule we would need in order to get this product from an ozonolysis reaction. When you do ozonolysis, you replace a carbon-to-carbon bond, and it can either be a double or a triple bond, with a carbon-to-oxygen bond. Now what you'll notice here is that we have an aldehyde, not a carboxylic acid. That means that we're doing ozonolysis on an alkene. Oops, let me do this. That means that we're doing ozonolysis on an alkene. And so the alkene that we would have started with would have just been this one, where it got broken, it got cleaved by the ozone. The bottom half turned into what we have here. And the top half would have turned into formaldehyde. So the carbon, that's smallest of all possible aldehydes. Carbon double bonded to oxygen, single bonded to a hydrogen on each side. That's formaldehyde. Now that can diffuse away in the solution. But the part that we're interested in would become the final product that we have. So if we had that alkene, then we could do ozonolysis, and ozonolysis on an alkene is first you bubble ozone gas, O3, into the solution, and then you follow it up with dimethyl sulfide, DMS. So that's just a sulfur with two methyl groups, one on each side, dimethyl sulfide, acting as a reducing agent. So we noticed that the number of carbons went down. That means we had to have done ozonolysis. So we looked at our product and we thought, what material would we need? We sort of thought backwards. We said, to make this, what would we need? Doing ozonolysis, we saw that it was an aldehyde, not a carboxylic acid. That means that we needed an alkene, and where the oxygen was, we just replaced it with a carbon. And that bond would get cleaved in ozonolysis, leaving us with our product in the bottom part. Okay, so that's where we are so far. Now, if we number the carbons, you see there are 2 there. Notice that this bond has rotated a little bit, but those are the same 2 carbons. So what we need to do is to create a pi bond between carbons 1 and 2, just like we have here. We need to create a pi bond between carbons number 1 and 2. That means that we have to do an elimination reaction. Elimination reactions are how you create pi bonds. But unfortunately, we have an OH there, but we don't have a good leaving group. OH is a bad leaving group. Now you might be tempted to say, okay, well, what if we added concentrated HCl? We could do a proton transfer, turn this into H2O, right? If that accepts an H plus from the sulfuric acid, then it's a good leaving group. It could leave as water. The problem is that that is an SN1 reaction and always gives you the Zaitsev product. So notice that you could get 2 products doing an elimination reaction with this oxygen. You could form a pi bond toward the beta carbon on the left, or you could form a pi bond toward the beta carbon on the right. We want to form it on the right. These 2 are the same molecule. Maybe that's a little clearer if I erase this hydrogen. These 2 are the same molecule. That hydrogen's still there, it's just implied in the skeletal structure. Remember, these single bonds can rotate. If you rotate this bond, you end up getting this structure on the left. So those are the same molecule. We want to form this elimination product. And that elimination product is the Hofmann product. Think about how substituted each of these alkenes are. The one on the left has 1, 2, 3 carbons attached to the carbons in the double bond. That's tri-substituted. The carbon on the right has just 1 carbon attached to the double bond, to carbons in the double bond. That's mono-substituted. And so the one on the left is the Zaitsev product. The one on the right, the left substituted one, is the Hofmann product. E1 reactions, the type of reaction you would do if you used concentrated sulfuric acid, turn this into a good leaving group that comes off first. E1 reactions always give you the Zaitsev product as your major product. But here we want the Hofmann product, so we cannot do this E1 reaction. Instead, we have to turn this into a good leaving group another way, and that is a way we've seen in a previous video. Because it takes a little time to explain, I'm not going to explain it again here, but it is in a previous video for this chapter, that was you can use 4-toluene sulfonyl chloride, TSCl, followed by pyridine. And what that does is it turns the OH into a good leaving group. Technically, what it would look like is, and here, let me just get rid of this, and then this. What it would look like at first is you would just replace the H with a TS. So that's called a tosylate. And this now, that is a great leaving group. This is a really good leaving group. So we can turn that into a good leaving group, and now we can do an E2 reaction. Now we can get this Hofmann product, the less substituted product, by using a bulky base, as we've seen many times before. Now because these are the same, I'm just going to draw it over to this molecule we already have. That's the same thing as this one, so I'm actually going to get rid of this one. We can form that less substituted product by using a bulky base. The bulky base you would want to be familiar with is potassium tert-butoxide. So here, if someone asked you how to do this transformation, you could say, well, first, you need to do an elimination reaction. You need to do an elimination reaction because the number of carbons decreases. That means you have to do ozonolysis. And because you made an aldehyde, not a carboxylic acid, you did ozonolysis on an alkene. So replace the oxygen with a carbon. That's the alkene you need to do ozonolysis on. To make that alkene, the only way you can make a pi bond on a molecule that doesn't have one is to do an elimination reaction. But we don't have a good leaving group. So the first thing is to turn the OH into a good leaving group by adding 4-toluene sulfonyl chloride, TSCl, in pyridine. Once you have that good leaving group, you can form a pi bond in the less crowded direction using a bulky base, potassium tert-butoxide. And once you have that pi bond, you can do ozonolysis to saw off that one carbon. So that's two steps. First you bubble ozone gas through it, and then you mix it with some dimethyl sulfide. So that this recipe would accomplish this transformation. So in exercise 1210, we've sort of explored and sharpened our skills in thinking through these, in building connections between these reactions. Two important patterns that we've seen so far are making a carbon chain longer by using a terminal alkyne, sodium amide, and an alkyl halide. That's one. Making it shorter by doing ozonolysis. That's two. And turning an alkene into an alkyne by adding bromine, excess sodium amide, and water. That's three. Three big patterns that we've sort of practiced. And we've mixed those in with other individual reactions from the alkene and alkyne.